Well, good afternoon. Um, has everyone been able to navigate the exercises that Mr. Lau has suggested? Don't forget that you can choose your own exercises, and including things that just have come up in class. For instance, if the K1, K0 of a field is isomorphic to Z, implies K0 of a field, let's call it plus the image of the semigroup, the canonical semigroup that's used to define K0. Okay, is isomorphic to Z plus, Z plus. Okay. Okay. And the point of this is that it's an example of another example of two basic statements, two basic linear algebra statements that are that are equivalent. And so non-trivial statements that are trivially equivalent. And so this, of course, implies this, because this is just the enveloping group of that. But if you have the group, you're not quite sure what the semigroup is that it comes from. It might be the whole group. All right. This is a good exercise, and from this, it follows immediately from the definition that that the number of elements in a basis, for instance, for finitely generated vector space, is always the same for any basis. Okay, so this would be a good exercise. And let me repeat a hint that I may have given. This semigroup, by a trivial linear algebra theorem, you know that every vector space is the direct sum of copies of the field. That's the same as saying there exists a basis, without knowing how many elements there are in it. But that means the semigroup is just generated as finite sums of the single copy of the field. Okay, so it's the semigroup is singly generated. It's a semigroup generated by a single number, single element. Okay, single element, and and that can be used. That can be used to show that if the group that it generates is Z, then then this is what it must be. Okay. And okay, so that's an example of an exercise that you could choose, which is not on Mr. Lau's list, I guess. Right. Something that was on his list is something that's fairly tricky. In fact, that now it's about spectrum or about invertibility. If you have suppose you have two unital algebras, two unital rings. You say algebra. We'll say C-star algebras, because the rest of the question is about the C-star algebra case. The trivial statement is that if two algebras are isomorphic, and then this map preserves spectra. Preserves invertible elements. That's the same thing. So if you have an element which is invertible in one ring, then its image under the isomorphism will be invertible in the other ring. Of course, since you can go both directions, that's the arrow goes in both directions for the isomorphism. It's if and only if. But if you're talking about a map between C-star algebras, in the particular question that came up from that Mr. Lau recommended from the book, the two algebras are not arbitrary unital rings, unital algebras, but the algebra map is not an isomorphism. Okay, it's assumed to be injective. It's a C-star algebra homomorphism. It preserves the star operation, preserves addition, scalar multiplication, and multiplication of two elements. But it's not assumed to be surjective. It's assumed to be injective, but not surjective. And the question was to show that it preserves still preserves the spectrum. Okay, it's, and so in other words, an element, if it maps from A into B, then an element of say the map is phi. The element A of little a of A is invertible. The little a is invertible if only if phi of A is invertible inside B. And of course, phi of little a belongs to phi of big A. Okay, and phi of big A is not necessarily equal to B. So we're assuming it's an injective map. Okay, so what's the notation for an injective map? Well, let's just say injective. Okay. Well, if it were surjective, then we'd be finished. But not only is it not surjective, we don't even know that the image is closed. We don't know that the image is a sub-C-star. We don't know the image is a C-star algebra. If it weren't closed, it wouldn't be complete. It wouldn't be a C-star algebra. If it were a C-star algebra, well, there's a theorem about C-star algebras. If you have, if A is a sub-C-star algebra of B, okay, so it's the inclusion map. Inclusion map is preserves the star operation. It preserves the well, of course, it preserves the norm of the subalgebra, but it's closed. The closed sub. It's a sub-C-star algebra. That means it's a closed the star subalgebra. All right, so but then okay, so if it is true, if it is a sub-C-star algebra, then if A belongs to if A belongs to big A, little a belongs to big A, then A is little a is invertible. It's invertible in capital A. It's invertible in the algebra A, if and only if it's invertible in the big algebra. It's invertible in the subalgebra. So this is notation. A minus 1 is the commonly used notation for the invertible element, a set of invertible elements, which of course is a group. Okay, so if you know this, then you're almost in business, except you don't know that phi of A, it's contained in B, but you don't know it's closed. Okay, well, so what you do is prove that the map is isometric. prove it's isometric. And then the image will be closed, right? Because it's yeah, if because is that clear? As an exercise. I mean, I could, if I have to work up a little energy to say it. Okay, say why. So, and I have a feeling that whenever that happens, that's a good time to suggest an exercise. Okay. Of course, I have to use my judgment because I don't want to be suggesting too many wrong statements as exercise. But on the other hand, maybe okay. Well, this is not one, but maybe it doesn't hurt to keep an eye out for peccadillos, minor or major, or minor or less minor sins. Okay, so now let me say what the strategy is to prove that the injective star homomorphism, injective C-star algebra homomorphism is isometric. In one sentence, the clue, the strategy, the effective strategy is to reduce to the commutative case. Okay, reduce to the case that both A and B are commutative, because then you can apply the Gelfand-Naimark theorem for commutative C-star algebras. It reduces you to just continuous functions on a topological space for A and for B. Okay, so that's that's a hint. Okay, so so in other words, it's easy in the commutative case from using the just working with functions and the fact that, well, if you know that A and B are just continuous functions on two topological spaces, two compact spaces, then the map from A to B then is equivalent to a map from the space for B to the space for A. Okay, continuous map. And you just have to prove that if the map forwards is injective, that's always true, whether the map forwards is injective or not. Then you just prove that the map forwards being injective is the same as the map backwards between what are called the spectra, the algebras, the spaces. So you have C of Y and C of X. Okay. So you have maps going forwards, unital maps going forwards are the same as maps going backwards, which from the Y to the X, continuous map going backwards, and the map going forwards is injective, if and only if the map going backwards is surjective. Okay, and a good question might be not pertinent, but the good question might be, what about the map going forward being surjective? Is that equivalent to the map going backwards being injective? And doesn't this sound a bit like what I was saying about finite dimensional vector spaces? That if you want to prove that the two statements in linear algebra for finitely generated vector spaces, that the injectivity of a map implies surjectivity. That's one statement. The other statement is surjectivity implies injectivity. Okay, those are trivially equivalent, and the trick is you go to the dual, which is linear functionals. By the way, these can be expressed as certain linear functionals, extreme points of the unit ball, positive linear function. But then passing to the dual, it just interchanges injectivity and surjectivity. Okay, finitely generated transformations on a finite dimensional vector space, and passing to the adjoint transformation, which just means an actual map in the opposite direction. Okay, so that's how you deal with the that's a outline of what you should do to prove that classify as isometric, because once you know it's isometric for self-adjoint elements, then you know use the C-star algebra identity. And here you reduce to self-adjoint elements too, because and one of the exercises is that x is invertible if and only if x star x and x star are invertible. Okay, one of the suggested exercises, and so it's important. So it's important to look at a self-adjoint element. If you get a self-adjoint element, uh, then if A is self-adjoint, then there's always a sequence AN converging to A, and AN is invertible. Okay, whether A is invertible or not, AN is invertible because you just add a complex number. You add an imaginary number. You small imaginary number. If A is self-adjoint, then A plus P times I is invertible. Okay, for arbitrary non-zero T. Okay, so so let's assume that that A is an element of little a. Oh, sorry, little a is an element of large A, the subalgebra, and assume it's invertible in B. So assume that that A belongs to B inverse. A is an invertible element in B. Okay, but then it's still true that AN converges to A, right? AN converges to A in capital A, then in the it's the subalgebra of B. So by the way, now this is a Banach algebra term. If I have the AN converging to A and the AN are invertible in the subalgebra, it could be true for we're just talking about Banach algebras now. The C-star algebra case is reduced to the Banach algebra setting using self-adjointment. Okay, so if AN converges to A in B, well, in B you have A inverse. Okay, you have so in the Banach algebra, in the C, where they say C-star algebra if you want, if you have a bunch of, or just look at operators, if you have a bunch of operators or elements of the Banach algebra converging to elements of the Banach algebra, and if everything in sight is invertible, the elements of the sequence are invertible as they are here, because they're invertible in the subalgebra. And if the limit is invertible, as it is by assumption in the large algebra, then the inverses converge to the inverse. That's just like that's calculus, okay? A bunch of functions. You can prove a bunch of functions converge to a invertible function on zero values on the interval 0, 1, then the inverse will 1 over the function will converge to 1 over the function. That's, you have to prove it, okay? It's not quite trivial, but you have to prove it. It's true in calculus, it's true here. A lot of terms in calculus are terms in Banach algebra. So for instance, the definition of the exponential, okay, that's not pertinent exactly here, but just the power series converges in any Banach algebra using complete. Okay, the same arithmetic is in for real numbers. All right, so AN to -1 converges to A to the -1, but A to the AN to the -1 belongs to A, and A is closed, so B A inverse belongs to A. That's how it goes. Okay, got question. Are you Chicam?
Yeah.
Okay, well, right, I can see that, yeah. But I could see that immediately. I couldn't quite see immediately. I wasn't sure. Okay, but all right, but no, but of course, yeah. And what is the question?
Suppose you have a unital C-star algebra algebra that no one can.
Well, it doesn't contain the unit of the whole algebra, because in the finite dimensional case, every finite dimensional C3 algebra has a unit, not necessarily the unit of the larger algebra. Okay, but you take the zero subalgebra. No, well, that's a good question, but remember, you should pinch yourself before you think you can't answer a question. To make sure you're awake. Well, no, I have to do that all the time. I mean, it took me a long time to remember that you do this by reducing to the commutative case, okay, which makes it easy. It's just following your nose now, putting one foot in front of the other. Okay, so let me run through people's names. Try to do it fairly quickly. I was supposed to measure people's participation somehow and asking questions, even questions where the guy forgot to pinch himself. That's okay, because it gets things started. Okay, and so answering questions and then coming after class to ask a question that you didn't ask during the class, although I would like to welcome questions coming up during the class too. And then, well, is everyone aware of the tutorial that Mr. Lau is running on Friday afternoon from 3 to 4? So it's in a certain room upstairs, just on the math floor, for 6180. It's opposite the big seminar room, the small seminar room, the meeting room. Okay, so well, so that's participation. And by the way, you could join. I forwarded an email about the study groups, right? So you could form a. You can always, well, everyone has a study group of one, but you can have one of two or three or four, and even do it under the aegis of the university. I guess they got tired of complaining about people doing homework together. Okay, but so Abigail Arsenal, oh, thank you. Alexander Bullen, thank you. Jing Quan Cao, thank you. Jack Cerrone. He was asking me after class about this one the exercise I just talked about. So I especially I wanted to direct my comments to him. But does anyone know him? Dr. Okay, but why not let him know to try the commutative case? Do the commutative case first, and then see if it can reduce to that. So that's the basic thing. And so let me just check names. You're Charlie, and I did. You came around last time, but I forgot you. I don't know if I asked you. Arcaprava. Okay, we just corresponded recently, so I got your name on the list now. I mean, I put it in myself, but I didn't. Yesterday. It wasn't on purpose, but we'll see what happens. Oh, good. Well, what I like to see is people who have to struggle to get in the course. That That's almost as bad as a comment when I was a postdoc at UBC, and there was a guy who would organize hikes. And then, of course, a lot of the year hike in UBC, hike in British Columbia means snow, walking in the mountains, getting snow. And so, but anyway, at the very beginning of the walk down below, one of the participants, who a recent faculty member, had new boots. So were obviously new boots. And so the tour guide, I mean, the one who was the faculty member who was taking senior faculty, moderately senior faculty member who was taking the tour, he said in a kind of quite nasty way, "That's what I like to see, someone with new boots." Okay. Yuja Cheng, thank you. Carissa Cho Lee, thank you. Siddharth Dagar, thank you. Daniel Dima, Emil Fredfeld. Did you just put up your hand? Oh, okay, sorry. It's I wasn't quite awake, and it's a bit dark. Once I start complaining about something, I can't stop. So maybe I better not start. Okay. Justin Food, thank you. Sabek Jermaine. Charles Griffin. San May Grover, thank you. Henry Hu, thank you. Zhao Hua Huang, thank you. Delao Casa, thank you. And please forgive me for more minor, well, I hope minor peccadillos of this pronunciation. Alexander Ko. Zhao Shang Lin, thank you. Yifei Lu. It's already sort of rewarding that someone puts up their hand when I mispronounce the name. Okay, so that's but I shouldn't go false confidence. Luke McCutcheon. Abu Bakar Zohid. Thank you. Thank you. Manariso Mulaisho. Ruben Navasarja. Jonathan Ing. Rishi Prakash. How are you on Shi? HY. Hotel Su. She Shijuo Sun. Lawrence Tsai. Amy Wang. Aaron Wang. Are you Aaron Wang?
Oh, yeah.
Yeah,
Yes.
okay, yeah. All right, well, I didn't need to ask. Hongbo Wang. Yeah, thank you. Xiaodong Wei. Chikan Wang. Jiqi Zhang. Okay. All right, well, today I want to, I was planning to continue talking about Wynn's work on in the PhD thesis, the UHF observation tensor products of matrix algebra, including finite tensor products, including just ordinary matrix algebra. Remember, finite tensor product of matrix algebra is another matrix algebra where you just multiply the orders. So M2 tensor M2 is M what? Or is M2 tensor M2. If it's a single matrix algebra, which one is it? Okay. I guess I sometimes say things too fast. What I said was, if it's so if you say Mn, then n is sometimes called the order of the matrices, okay, or the size, okay. So you take 2 by 2 matrices and 2 by 2 matrices, then what do you get? You take the tensor product. Well, what's the linear dimension? What's the linear dimension? Pardon? Well, yes, of 2 by 2 matrices, the linear dimension is 4. Okay, and you take the tensor product of 2 vector spaces. I guess what happens to the dimension if you take 2 finite dimensional vector spaces and take the tensor product? Okay. Sorry, I can't hear you. Sorry. If you take vector spaces and take the direct sum, then you add the dimensions, right? But if you take the tensor product, then what do you do? Yeah. That's so. But then that means if you look at the now remember that the Mn is not the dimension. N is not the dimension of the algebra considered as a linear space, right? It's just the order of the matrices. It's n by n matrices, and sometimes you write n by n with a multiplication sign in the middle, right? So that I don't know if that's the purpose, but if you're calculating the linear dimension of n by n matrices, then you just multiply the n and the n. And if it's n by n matrices, you just multiply the n and the m, right? And that gives you the linear dimension. Well, and so and you take the tensor product, if the dimensions get multiplied, then the square root of the dimension also gets multiplied, right? So M2 tensor M2 would be, if it's M something, if it's M sub n, what's n? Well, the linear dimension is 2 squared, okay? 2 squared times 2 squared is 16. Well, you take the square roots, 2 times 2, 2 times 2 is 4, right? Okay, so, but this is an exercise, I mean, this is not a proof that tensor 2 by 2 matrices, tensor 2 by 2 matrices, this is not a proof that it's isomorphic to M4, 4 by 4 matrices, right? That's an exercise, you have to prove it somehow. But that's quite fundamental for studying UHF algebras, the infinite tensor product. Okay, so that's maybe the that's maybe how you that's maybe the sort of foundation for studying Gun's work. The idea that if you, and so what that means in particular, if you look at matrix algebra, I don't know what someone would do who's less heavy than I am. Well, I guess they would be doing chin-ups, right? Okay. So if you look at Mn, and well, that means looking at n in particular, right? All right. Well, n, if n is a natural number, say not equal to 0, then it's equal to 2 to some power. Let's say the exponent is e sub 2, and then it's times 3 to the exponent e sub 3, and 5 to the e sub 5, and then some finite product of prime powers, right? And furthermore, that's a unique expression. You have to work a bit to get it's not too hard to prove that the decomposition exists if you know prime numbers are the same as numbers that can't be factorized in a proper way. But to get that it's unique, okay, well, that's, I don't know whether you should say it, yes. Well, it's number theory, right? I mean, it's a, you don't have to quote a theorem, it is a theorem, right? It's a, you're quoting a more general theorem, maybe. All right, but if the integers form a unique factorization domain, is that what you were going to say? Yeah, but but that's just that's in the philosophical use of the term. I think that's just begging the question, and coming back to the beginning. My lexicon, begging the question doesn't mean asking, inviting the question. It means somehow trivializing the situation. Well, okay, so, but it's a unique factorization in terms of primes, a well-known prime number. Okay, but then how does that, so that means that Mn is equal to M2 to the E2, 3 to the E3, 5 to the E5, so on, and finite product. But that's a trivial statement. That's just carrying over the factorization of the number. But if we were going to, Carissa, how would you interpret that in terms of the tensor product of matrix algebra? And I hope you've had time to bone up on your arithmetic in the meantime. I'm sorry. Okay, so what is the answer? Yeah, so so it's isomorphic if we agree that M of N1, N2 is isomorphic to Mn1 tensor Mn2 for any natural numbers N1 and N2, then it would be M to the 2 to the E2 tensor M to the 3 to the E3 tensor so on, okay? And you could even, we could even split up the prime numbers too. We could just say it's M2 tensor M2 certain number of times, E2 times, and then tensor M3 certain number of times, and so on. Okay, so just as every natural number is uniquely a product of prime numbers with repetition. The just that's also true for the matrix algebra. Just, every finite matrix algebra, some order is a tensor product, isomorphic to the tensor product of a finite number of matrices of prime order. The finite number of matrix algebras of prime order. And furthermore, this factorization is unique up to order, of course. You have to be a little careful because multiplication of numbers is actually commutative. That multiplication tensor product of algebras is not quite commutative. It's commutative up to isomorphism, but that's not right. Yes, Sarah. That isn't that supposed to be okay, so E2 of the 2s and E3 of the 3s?
Yeah, it should be M3 tensor, M3 tensor 2, like this E3 number, but not 2, right?
Well, okay, but I don't know what E3 is exactly, so I couldn't write them all down.
Oh.
I just wrote the first one. I should have written the last one too, maybe.
Oh.
Oh, but there's a finite number. finite number of M2s. There's an E2 M2 and E3 M3s, and so on. Just put them all down in a row.
Sorry, so that's E2. You said that's E3, not E2.
I was getting a little sloppy in my handwriting, okay?
My fault.
Well, maybe not clear who's the fault. Yeah. Right. Okay, so it's like leaving something unsaid. Oh, there's a difference between leaving something completely unsaid and saying it in a careless way. Don't know which is worse? Maybe it depends on the situation. All right. So, but then now the next thing is to do the case where n is infinite. Okay. What do I mean by that? This is what Grimm did in the terminology of in a formulation explored by Dijksma. So Dijksma wrote a paper which was it was one of the things forming my whole career, if you like. It was a 1967 paper. It was in volume 1 of the Journal of Functional Analysis. I was supposed to be studying functional analysis, and I was a graduate student then. That was my first year as a PhD student here. And, all right, so it still resonates inside my head. I hope I can recreate the same phenomenon with some people. Okay, so well, Dijksma formulated a meaning to n being infinite in this context. He called it the generalized integer. Okay, you have natural numbers or integers, and then you have Dijksma's generalized integers. And what they were, it was a formal definition. It didn't actually. He took a whole lot of prime powers, 2 to the E2, and you even allowed E2 to be infinite. And so you basically just, it's a sequence of exponents, and then 3 to the E3, and 3 there, 5 to the E5. You're basically just looking at the sequence of exponents. And each one can be equal to 0, 1, 2, and so on, up to plus infinity. But you're not trying to really, you're not physically trying to take prime number 2 to the power 0. Well, you can take it to the finite powers, that's well known. Taking it to the infinite power, that's just a way of speaking. Okay, the meaning you look at the exponents, and so that's so a super. So a general Dijksma's generalized integers, he always wrote them as n is 2 to the E2, 3 to the E3, 5 to the E5, and so on. It's the infinite product. The dots in between them if you want. Then you have to keep the single dots separate from the sequences of 3 dots. Oh. Okay, but that, and a topology guy who was visiting Copenhagen for a while, kind of a smart aleck, there wasn't before the EU, it was just a common market. But he went to visit Germany and didn't take his passport. He didn't bother taking his passport. He just took his Danish insurance card. But he was such a smooth talker, he didn't get into any trouble. And this is Larry Smith, very, very helpful as an operator Algebras as well. Followed his wife with similar interests, Miso Bai Smith. So his suggestion was to call these, well, you have the ordinary natural numbers, and these are the supernatural numbers. Okay. And they exist perfectly well. They're just infinite sequences of not zeros and ones, but zeros and ones, and all the way up to allowing infinity, plus the infinite number. If you call it L0, it makes no difference. And so if you allow the finite ones too, then arbitrary sequences are allowed, okay? But if we were sequences of zeros and ones, we know there's an actual topology, right? What's the topology of Elon? Or Alan, how do you pronounce your name? I was thinking it was just Alan for a while. Ellen, okay, good. Well, so what's the natural topology on sequences of zeros and ones? Okay, well, it's a Cartesian product of 2-point spaces, right?
Yeah.
So any Cartesian product of topological spaces, there's what's called a product topology, right? Finite, it's a little more well known if it's a finite Cartesian product. If it's infinite Cartesian product, doesn't make any difference. And furthermore, if it's compact spaces, then the Cartesian product is compact, right? And if the individual spaces are totally disconnected, that means the basis of open and closed sets, then the Cartesian product is totally disconnected, right? And if in certain cases, if it's infinite sequences of zeros and ones, it's well, if it's any finite, if it's any okay, but if it's a completely discrete space, then it's sort of clear that the infinite product doesn't have any isolated points, okay? So it's the Cantor set. It's not just, it's more than one point to start with. But it's a good exercise that you get the same topological space. Remember, the Cantor set is unique with certain properties as a compact metric space. We just have to prove that the infinite Cartesian product of copies, thank you, infinite Cartesian product of copies of this space. Yeah, of this space are is the Cantor set. So that means we have these algebras then. The algebras m sub n. The n sub n is just the infinite tensor part of all these. They're naturally parametrized by the Cantor set. Okay, and in fact, I'm going to turn that into what's called a continuous field of Cauchy algebra, but that'll have to be another day. But I guess there are people coming in now, but outside in the hall we can talk for a while.